Welcome to this explainer. Okay, today we're going to break down a literally game-changing architectural hack to help you slay what I like to call the cloud bill monster. If you've ever tried to run your own applications in the cloud, well, you know exactly what I'm talking about. We're looking at a brilliant strategy to keep your apps running flawlessly without totally draining your bank account.
So here's the big question for us today. How do you keep your personal or side projects highly available, fully resilient, without paying those absolutely exorbitant enterprise-level cloud fees? I mean, we all want that peace of mind that comes with a system that just fixes itself when it crashes. But the traditional tools to do that, they're usually built and priced for massive corporations.
The numbers really speak for themselves here. We're talking about taking a cloud bill from around $150 a month all the way down to just $40 a month. That is a massive drop. In our source material today, a developer details how they were running a background hobby project on Google Kubernetes Engine, or GKE. And sure, it was solid, it was trouble-free, but it was costing $150 a month. For a side gig that doesn't even strictly need 100% uptime, that's just way too much. But by shifting to a highly optimized setup, they slashed that bill to $40 while keeping the automated recovery. Let's look at exactly how they pulled off this technical magic trick.
Here is our roadmap for this explainer. First, the Kubernetes cost trap. Second, stateful MIGs to the rescue. Third, surviving spot VM preemption. Fourth, preemption versus scaling down. And fifth, the local to cloud toolkit. Section 1. The Kubernetes cost trap. Powerful, but pricey.
The developer-specific pain point here really hits the nail on the head. Running just a couple of preemptible nodes with a managed ingress was still running them $150 a month. Now, Kubernetes is the industry standard for sure, but it is complete overkill for a simple project. You end up paying for the cluster management overhead and those pricey managed ingress load balancers. Sure, you get incredible self-healing capabilities, but you definitely pay a premium for it. Okay, let's dive into this and compare the options. On one side, Kubernetes gives you that sweet automatic recovery, but with really high compute costs. Now, a standalone VM drops the cost way down, but you lose the automatic recovery. If that VM dies, you have to manually recreate it. But look at the stateful MIG, the managed instance group, using a spot VM. This sits perfectly as the ultimate middle ground. It gives you the lowest possible compute cost by using spot VMs, but it completely retains the fully automatic preemption recovery of Kubernetes. It's literally the best of both worlds.
Section 2. Stateful MIGs to the rescue. Decoupling compute from state.
All right, so the fundamental architectural trick here is separating the volatile brain, the computing power itself, from your stable, permanent assets. This brings us to a concept called storage state preservation. When you boot up a standard virtual machine, storage targets like, /dev/stp are loaded dynamically. They actually swap order during initialization. It's kind of like shuffling a deck of cards. You just can't guarantee what order they're going to be in when they're dealt. If you rely on those dynamic targets, your automated recovery is going to fail because the system literally can't find its own data.
So the crucial point is this. Instead of using a target that shuffles around, this architecture targets the persistent volume via its unchangeable physical serial header. You use the exact path, /dev/disk/by-id, followed by Google-existing-data. Because this targets the actual hard-coded ID of the disk, it acts as an absolute permanent anchor for the data. No matter how many times the virtual machine gets destroyed and recreated, the startup script is always going to find the right data.
Section 3. Surviving spot VM preemption, the magic trick.
Now you might be wondering, what happens when Google Cloud inevitably preempts and just kills your cheap instance? Well, the magic happens through a fully automated workflow. I want you to think of the managed instance group almost like a hyper-vigilant robot manager. Step 1, detection. The MIG literally spots the deletion of your instance. Step 2, provisioning. It instantly orders a fresh node. Step 3, stateful attachment. The MIG just knows exactly what to do. It dynamically hot plugs your regional, static IP, and your persistent disk straight into the new node. Step 4, bootstrapping. Your custom startup script takes over, mounts the file system, installs Docker, and restarts your microservices. And step 5, boom, your system is back online.
And this brilliantly illustrates the true power of this setup. This whole complex recovery process, detecting the failure, provisioning the new machine, hot plugging the storage and IP, and bootstrapping the apps, it brings the platform completely back online in just 60 to 90 seconds. And it does this with zero manual intervention. Your cheap little cloud infrastructure is now fully self-healing.
Section 4.
Pre-emption versus scaling down, a vital operational distinction.
Okay, if you're actually going to implement this, there is a massive difference you need to understand between an automated cloud eviction and explicit manual human intervention. A true spot preemption is entirely different from you doing a manual scale down to 0. When Google preempts your VM, the MIG's intent is still to keep one machine online. Your configs are preserved, recovery is totally autonomous. But if you manually scale the group down to 0, say, to save money, the MIG's intent changes to decommissioning the app. Crucially, those unique stateful metadata ties are completely wiped out. If you just scale it back up to 1, the new VM is going to get stuck in an endless boot loop looking for a disk the MIG forgot about. To fix a manual scale down, you have to run a manual orchestration script to explicitly rebind your static IP and your data disk.
Section 5. The Local-to-Cloud Toolkit, Building the Blueprint. So what are the actual nuts and bolts required to piece this clever infrastructure puzzle together? Well, the developer uses a pretty simple modular blueprint of bash scripts. You've got your startup script, which handles that hardware mounting and Docker installation we just talked about. You have create-mig, which acts as that manual orchestration script to rebind your IP and disk if you ever do scale down to 0. And importantly, you have start-traffic. Remember how managed Kubernetes ingress was a huge chunk of that $150 bill? Here, the developer completely replaces it by running a traffic reverse proxy alongside Let's Encrypt to handle the SSL certificates. The whole shebang is orchestrated via simple shell scripts.
Let's move to how this builds out, because this modular setup creates a massive advantage for the developer experience. By ditching those super complex Kubernetes pipelines that need Minikube and Cloud Build and shifting entirely to Docker Compose, you achieve seamless local-to-cloud parity. The exact same scripts and YAML files that run locally on your Mac are the ones running remotely on the cloud VM. You literally get a complete end-to-end simulation locally before you ever deploy it to the web.
So what does this all mean for us? We've seen how separating state from compute, targeting actual physical disk headers, and leveraging managed instance groups can create an amazingly resilient system on a total shoestring budget. Which really leaves us with this final provocative thought to ponder. If a simple $40 setup, using Docker Compose and Spot VMs, can autonomously self-heal exactly like a massive, expensive Kubernetes cluster, are you currently over-engineering your own cloud infrastructure? It definitely makes you look at those heavy enterprise tools in a whole new light, doesn't it? Thank you so much for joining me on this explainer, and I really hope this sparks some great ideas for your next project.